I think we are not seeing any physicists right now, except for you. Well, I'll just start the introduction because there might be people joining in. But I just wanted to welcome all of you again for this edition of the Wednesday Colloquium. And one of the things that, you know, you fight every day and you work hard every day and you realize that, it's always a tough life you are leading. You have to battle things. But sometimes when you meet people like Mahesh, you feel very lucky that, oh, you have good friends like him. And this is exactly what I feel when I see Mahesh. Um, uh, he's one of those individuals who actually kind of makes me feel that, okay, I'm lucky to have friends like him. And it's, um, it's a pleasure, Mahesh, to have you here for the Wednesday colloquium, just for a sake of formal introduction. And the colloquium was started by Professor Homi Bhabha. It was sort of under the aegis that people would get together in all the sciences faculty would get together on Wednesday and meet Professor Bhabha and also organize this colloquium where everybody could attend. And this has actually kept the physicists, chemists, and biologists together, at least for that few moments, so that they can have this more rigorous discussions after the colloquium with the speaker or within themselves. So there's been a very good tradition for all of us. Students have been trained to be broad-minded with this kind of a, training. So I'm very happy that you're giving this colloquium for us. Of course, without further delay, I just wanted to give a little bit of an introduction to Mahesh's background. Currently, Mahesh is, of course, a professor at the School of Chemistry in IISER, Thiruvananthapuram. He did his PhD from 2002 to 2007 in NIIST, India, and this was with Professor D.D. Ramaya. And during this time, Mahesh actually got accustomed or used to making molecules and looking at very interesting, weak interactions and supramolecular properties of these molecules, and also was sort of looking at how to sort of design methods to characterize molecules as best as can. Also looking at photochemistry of these molecules. Mahesh then went to Fred Lewis at Northwestern University, where his research efforts were to focus to understanding of interaction of light with biomolecules, crystalline, and sort of biomolecules, mostly in DNA cases. But he actually had enough experience to come back based on this classic photochemistry training that he did with Fred to come back in India to start an entire new program, research program, physical chemistry based research program, where you could design conjugated molecules with different properties based on their morphological, control. And this is something that brought at least Mahesh to forefront, that he could sort of have a very fundamental understanding of how self-assembly takes place in pi conjugated molecules and how does that manifest into photophysical properties. And this is, he has been an advocate of understanding molecular properties and especially relate them to spectroscopy. Mahesh, for his fundamental work, some of it that he will talk about today, he has been sort of awarded and rewarded in various capacities. He was awarded the CRSI Bronze Medal in 2020. He won the Lectureship Award from the Japanese Photochemistry Association in, again, 2020. And then he sort of was one of the recipients of the Asian and Oceanian Young Photochemist Prize. Also, Mahesh is he's a fellow of the Indian National Academy, and he has been, of course, one of the important people in also being an editor in journal space in the Royal Society journals. One of the really good things about Mahesh has been that apart from all these sort of academic research activities, Mahesh also does a lot of outreach, and especially around the area in IISER Thiruvananthapuram. Mahesh has been heavily invested in taking science to colleges and schools. So I welcome Mahesh to give this colloquium, and thank you for coming, Mahesh. Thank you. And his talk today is on symmetry breaking, charge separation, something that he has pioneered in the field. Mahesh.
Yeah. Thank you, JD, for kind words of introduction. And also, thanks to colleagues, Professor Sudipta Maiti, Professor Kalobharan Maiti, and other colleagues in the department for extending this invitation. And it is wonderful to be around here. Since morning, I've been meeting faculty colleagues in the department. And also, it's a great honor to deliver this lecture, which is the TA for colloquium. For about next 35 to 40 minutes, I'll be talking to you about two aspects. One that you see. Am I doing everything right?
Yeah, it takes a bit of time for it to. Yeah.
Okay. Yeah. So now I see. So this is what we see here as Greek cross aggregate. It perhaps appears too much related to self-assembly or a chemistry related topic, but over a period of the talk, I would like to emphasize upon the fact that these are just two entities that come close to each other in a very peculiar geometry that has its own characteristic properties. And what is that peculiar geometry is something that I will elaborate upon for the first part of the talk. Learning lessons from nature, such as photosynthetic reaction center or DNA and various other biomolecules that I will touch upon in the beginning. And this particular architecture has something to do with symmetry breaking charge separation, which is what you see in the second part of the talk in chromophoric dimers. Again, the particular emphasis will be placed on photosynthetic reaction center and its implications thereafter. So moving forward, these are two interesting examples that we all like from the nature. So the first one, of course, many of you are well aware of, is the photosynthetic reaction center, where you begin with two identical chromophores, which are like, if you take two sodium atoms, there is no necessity that a sodium should be giving an electron to another sodium. So, but in turn, it happens in some of the occasions that you create this electron movement from one of the atom to the other atom in an identical pair, thereby generating a hole and an electron in such systems. And in organic materials, most of the time we call it as defects. While in organic systems or bioorganic systems, such whole electron pairs are welcome addition to the functions that are associated with it. So I will elaborate a little bit on the photosynthetic reaction center here. As you see, upon photoexcitation of this particular pair, you would see that you create a hole and electron, and the electron travels from the special pair, jumping from one unit to the other unit to the other unit to make the charges separated over a distance where 1 over r dependence of the Coulombic charges in terms of interaction energy makes it survive longer time. So the longer the distance that you have for the charges, the longer it survives. Now, no matter in the lab, when you synthesize such systems where the chromophores are periodically stacked and you have such kind of motion from one unit to the other, it appears that they recombine faster. And this is something that has been seen in many of the synthetic modular systems. However, in biological system, which is this photosynthetic reaction center, you see that the first two of them are cofacial in nature, meaning that two of the chromophores that are facing to each other. And then you place the wave packet on the first one. You have the electron moving from one unit to the other and creating the charge separated state, and the charges flow from one unit to the other until it gets separated over long distance, as you see over there. While this is not the thing that is easily achievable in laboratory, there are many laboratories who are trying to synthesize and emulate such charge separated states in organic supramolecular systems. Now, as you see here, these charges are used, of course, on one end for oxidation and on the other end for reduction, thereby converting carbon dioxide and water to sugars, which we all consume. Now, this being the case, that the function that you need from the photosynthetic reaction center as a catalyst, you need charges to survive longer. This is not what is needed in the case of nucleobases. So let us see another interesting biomolecule, which is DNA, that you see over here, wherein you have, let us say, a stack of A's and G's that are on top of each other, and you shine light on G. It has a very low ionization potential, and by virtue of that, an electron can get lost, and then it can jump to its counterpart, which can be C, or it can move through the stack of nucleobases that you have. And for this matter, there was a proposition in 1989 in a paper that was published in Science by a faculty from Caltech called Jacqueline Barton, and she proposed that every messaging signals that in our biological system go through DNA, and DNA is the platform to transport charge from one end to the other end. And this paper was quite exciting, and it just took attention from pretty much large scientific community, all to realize that DNA does not transport charge over such long distances in order to signal through the system. Although it was not precisely a scientifically accurate paper, but then the follow-up papers on that really established the fact that up to 4 nucleobases, which means that you have 4 of the aromatic hydrocarbons that are kept on top of each other. You inject charge on one end, you can have the charge coming from the other end up to 4 nucleobases, which means that you can have DNA acting as a conductor up to 4 nucleobases. But then if you have a prolonged DNA sequence up to 10 nucleobases, you can have the charges moving through this 10 nucleobases pretty much like a semiconductor. And anything beyond 10 nucleobases, DNA behaves like an insulator. And this is the current state of the art understanding about what DNA can do with respect to transporting charge from one end to the other end. And so is the case with exciton and the energy migration from one end to the other end. Now, this is possibly designed by nature in a manner that you don't want the movement of the charge or the survival of the charge on the nucleobases, because if that happens, let us take an example of G, and you create a radical cation of G, water surrounded by G would interact with G and create hydroxylated G, and that will eventually transform to 8-oxo G, which is something that is responsible for one form of cancer. And you can see that such modifications are rarely needed in genomic sequences. So therefore, the attempt by our body is to regulate such kind of oxidative process or charge creating processes. And therefore, in DNA, nucleobases are arranged in a manner that you don't want charges to survive longer. So you see in the first case, two of the chromophores that are just facing as a cofacial dimer, while in the case of DNA, you have a little bit of helical stacking between the nucleobases, thereby preventing a sort of gating for the charges to move around. So now the question that you can probably ask from these two examples is that why not having the nucleobases even crossed in a manner that you have 90° to each other, so that you have a perfect gate right now that the charge will not percolate through the stacks of aromatic hydrocarbons. And this was the original thought with which we began when we started our group in 2009 at IISER Thiruvananthapuram. And these two are natural examples. So you do not moderate the angle between the chromophores that are present in these molecules. However, when it comes to getting a precisely tuned 90° angle between two of the chromophores and letting or preventing the charges move through these stacks, it becomes a challenge just to get a material that has an angle like this. Now, this defines one of the boundaries of the charge transport, meaning that you don't have any charge that will transport if you have two of them crossed. Now, what if you have the other extreme, which means that you have a perfect stack on top of each other, which means that you have charge right now injected, and you would notice that the charge can percolate from the other side just because of the fact that they are perfectly on top of each other. Now, this sets the other extreme of whatever maximum charge transport that you can have in an organic or a bioorganic based system. And these are the two extremes that we started out working in our laboratory, just to define what could be the charge transport across these systems by preparing suitable examples. Yeah. Why it is not happening in cofacial? Why it is happening in cofacial
and not happening when the molecules are
yeah. So certainly, when I said cofacial could be the one that has maximum potential to transport charge, there is a limitation there. There is no way that we can achieve cofacial aromatic hydrocarbons to be sitting on top of each other. Although in photosynthetic reaction center it is nearly cofacial, the reason is that you have this orbital repulsion between any two hydrocarbons. So you keep carbon on carbon, which means that you have orbital on orbital, and that will make sure that there is a repulsion and it slips little bit. And any stable aggregate of hydrocarbon is little bit slip stacked, and that is the one that you can achieve maximum charge transport, meaning that experimentally you can get. Now, yeah, I mean, you have effective charge transfer component between two of them. As we progress along the line, I will try to give you an empirical approach to why these two, or else I can expand my introduction in the sense that I answer your question. So let us imagine that it's essentially same thing. I mean, I'm covering at some point in time. So let's say you have two chromophores that are at a distance of longer than 10 angstrom. Yeah, the only possible interaction between two chromophores could be such that you have transition dipole on one chromophore and the transition dipole on the other chromophore, and these two will interact. And this is what we typically call it as Coulombic interaction, because the transition dipoles are approximated to dipoles. So it is dipole-dipole approximation, and that's what we typically deal with, a Coulombic interaction. However, if you bring these two chromophores close to each other, you start seeing there is orbital-orbital interaction, and this can be quantified as charge transfer interaction. Now, any form of charge transport to happen in a given organic supramolecular system, you need to have charge transfer interaction stronger, which means that you need to have right orbital-orbital interaction, which is nothing but you need to have homo-homo overlap between two of the molecules and LUMO-LUMO overlap of two of the molecules, which will translate to whole transfer coupling and electron transfer coupling, the product of which leads to charge transfer coupling, and that's what corresponds to the charge transport across these molecules. So right now, through the contributions of Jean-Luc Bredas and few others in the literature, we clearly know a mapping of hydrocarbon where you can just keep one on top of the other and move them all along, like translational offset, and you can also have rotational offset. You can also bring them further further from each other, and in all possible directions, how much could be the charge transfer possibilities. This is well supported by Jenan Bavo from Stanford, measuring in some of the representative examples what could be the charge transport in these systems, and these two body of literature together explains pretty much like what drives the charge transport across the stacks of these molecules. I hope I have answered your question. Yeah. So the third example that we wish to discuss today is eumelanin, which is quite an interesting compound that we all know why our skin is colored, or why our hair is colored, or why our eyes are colored. But still, it's quite intriguing that we clearly do not know what is the origin of the color. And this is something that I will try establishing. And Debasri Ghosh from IISER Kolkata is working on the theoretical aspects of this, and she has done wonderful work in that area. While we try to approach this using our skill sets, which is basically synthesizing some of the analogous molecules in this direction, and then see what are the associated photophysics with it. These are the two magic molecules that are present in our body, which is called dihydroxyindole, the first one that you see over here. It's just a two aromatic ring containing compound. And then we also have another compound which has an additional carboxylic acid. And both these molecules are crazy that if you have just them in the solution, they tend to polymerize. And after a while, you will see that there will be a black material. And that black material is nothing but the black color that we all have in our skin, hair, eyes, etc. Now you try to protect, this carbon. That is, you have an hydrogen over here, replace with something, polymerization does not happen. You put a methyl group in this hydrogen, polymerization does not happen. And you put methyl group in this hydrogen, replace it, you don't have polymerization happening. So you can stop polymerization of this particular molecule through various means. However, when it polymerizes, we just do not know what it leads to. It forms a very dark material in the solid state, which is not soluble in anything except for doing solid state NMR. There is no spectroscopic characterization that you can have. However, the proposition at the moment for the color distribution that you have is, as you see, some of electronic transitions that you can have over a range of this entire visible wavelength. It should ideally be a dimer, trimer, tetramer, pentamer, or even longer than that, and you have a polymer of different conjugation length that is responsible for different wavelength absorption, and you add it up together, you should be getting either brown or black color that we all have. Yeah. So this is one possibility. The interesting thing is that this DHI, which is the first molecule, is the monomer is highly fluorescent. So imagine that this polymerization is not happening in our body. We will all be glowing in the night because of dihydroxyindole that is present. Yeah. And it goes to a dimer, goes to trimer. The fluorescence quantum yield gradually decreases, but it does not decrease to almost negligible value, which means that it has significant fluorescence, which also means that up to trimer is not what we have in our body. It is beyond that. Yeah, possibly. We still do not know. Now, to understand this, we propose two possibilities, meaning that you have either the monomer aggregating or the dimer aggregating or a trimer aggregating, because conjugation alone does not justify the color that we see, or the combination of absorptions that you see is not reflected in it. So it should be a combination of a conjugation and the aggregation that together drives the total color, and that is what we call as chemical disorder model. but we are in the process of now preparing longer analogs of this. So at some point in time, we will have a full story related to this. Yes. Yeah, because there is no way that you have polydispersity index of 1 in biological systems that you can achieve. So it must have, a combination. Again, the problem is that, the material that you get out of it by extraction is solid that you cannot characterize it. So it's generally presumed that these monomeric units combine to form a polymer. Fine. So this being said, let me move forward. That recently we also found another interesting literature. This is by Leah Adadi and co-workers from Israel, wherein they find that guanine, which we see in DNA, assembles themselves in order to form the scales of the fish that look silver, as you see the fish. So it is nothing but just guanine assembly that you have got. Yeah, so this range of biomolecules that you see, each of them are positioned or rather stacked in a manner that they have got certain interesting properties associated with it. And the choice of the fluorophore or the chromophore is also important in cases where you need to make them fluoresce. Sometimes you need charges that are to be harvested from it. Sometimes, you need to convert, putting light into it, you need to convert that into heat, and you don't want any more light coming out of these systems. So all these ranges that you see in nature that are being clearly developed with the choice of the molecules. And it is, nature has clearly optimized what is the molecule and what is the stacking that you require in order to promote such features. So here you notice that, JD has contributed a lot in terms of understanding bringing two pentacene molecules close to each other, and the so-called singlet fission is being tracked in his laboratory using ultrafast spectroscopy. There are several groups who are interested in looking at what happens if you have an electronic chromophore that is kept closer to another electronic chromophore. So for quite a long time, or still it continues to be, the interest was in taking an electronic chromophore, bring solvents close to each other, and what solvation dynamics can do to the chromophore. And this is a very interesting topic, and there has been a lot of exploration in that topic. However, our interest is to see what one chromophore molecule can do to the next one if it is kept near to it. And as you see here, building from a dimer to a trimer to a larger oligomer that are stacked on top of each other, which are not covalently connected, but they are just non-covalently stacked on top of each other. How would they behave? However, it's quite interesting that, many of the systems are disordered, as you see here, which we in general have very less information about, meaning that people have not understood how disordered aggregates behave. And there are a few groups who have started working on that. And we also have some results which are very preliminary in nature, and I'm not talking about that today. Now, this being said, I'm taking the example of only a dimer, and I will elaborate upon the possible diversity that exists in the excited state dynamics in one particular slide. So this is only about a dimer. So imagine that what complexities can arise if you move to dimer, or thereafter, it is only going to get more complex. So just to take dimer, as you notice here, the central one is a representative dimer, as you see here. Upon exciting one of the chromophores here, a wide range of processes that you can see that can get generated, in which, as you notice here, that there is a possibility that upon exciting a single chromophore, you can create two of the triplets in two of the molecules. This is what you call as multi-exciton generation, where for every photon that you give to the molecule, you create two excited states. And this is what JD has pioneered. While our interest has in this particular topic, where if you put excitation on one of the chromophores, you take an electron from one of the units to the other, and therefore you create a radical cation and a radical anion, much the same way like what we saw in the special pair of the photosynthetic reaction center. Now, what chromophoric orientation drives in order to get the charge separated states survive longer. As we all study that, charges are never stable by itself. So it has to recombine to get to the neutral state. And therefore, any effort to make the charges generated, they will eventually recombine. But do we make these charges survive long enough so that it encounters with the reactant molecules in the surroundings in order to react with it and convert these surrounding molecules to some useful form of chemicals from there? So that is one attempt that people worry about, creating charge separated state. These charges, when separated, you have the memory lost about the spin information on these molecules. While recombining, you can have the same singlet that is formed, but statistically, there is also a possibility that it forms triplet before it comes back to the ground state. So there are orientations of molecules that will allow the molecule to recombine back to the triplet before coming back to the ground state. And therefore, one such process is indicated over here, where this charge recombination leading to the triplet is achieved, and then it comes back to the ground state. There are also possibilities that you have the molecule excited, and one such chromophore carrying the excitation can delocalize the excitation to two molecules, and therefore you can have excimer generated, which means that the total energy that you have supplied to one molecule is now distributed to two molecules, two adjacent molecules. It can also go beyond that. I mean, this afternoon I had fantastic interaction with Amartya, who was talking about the model where you can have the charge, the energy that is placed on a chromophore can get delocalized over long distance as well instead of dimer. However, as you notice that what is taken here as a dimer model is just for the convenience sake, meaning that at the moment what we can easily understand is about dimer, but certainly it requires more effort to know about larger structures that can be generated from chromophores and molecules. There is also a possibility that you can have two of these triplets combining together in order to give the singlet back and then relax from the singlet excited state. So these are some representative examples that I have shown over here. There is a lot of debate on the last possible one that you see over here, which is coherence. So you place the excitation of one of the chromophores, it can oscillate back and forth between two of the units to have coherent oscillations, and that is something, what drives to get there and what is the right orientation between the molecule, how should the environment look like, how long these coherences can be set, is all now a matter of great interest on not only on photosynthetic reaction center, on artificially created dimer and aggregated systems as well. Yeah. Also
Working.
Yeah.
But is it really just a stochastic outcome of the wave function collapsing into either the electron landing on this side or that side 50% of time?
Yeah.
Is that so, or is it true that maybe there is slight difference between the two molecules that you put in so that it preferentially lands on one? Because I presume that ultimately you'd like to make it go one way and not the other. Like it happens in the natural photosynthetic system.
Yeah, this is quite an interesting question, and I would have completely agreed with you that it is just a statistical phenomenon that it distributes the charge on either side if this was observed on a gas phase. Yeah, meaning that there is no role of solvent. However, I think there were attempts in the past that people were trying to do such kind of measurements in the gas phase and did result in not observing the charges separated on either chromophores. And then this is a purely solvent-based phenomenon, which I will arrive at. And even in the photosynthetic reaction center, there is a role of some amino acid that is, just getting closer to the special pair that promotes the initial event of charge separated state. It is not just the chromophore orientation alone. So a very rudimentary picture of what is symmetry breaking is something that I am showing, but that is not comprehensive in terms of understanding what could be SBCS. Recently, taking two of the titles from our papers combined together, Frank Spano has published a very nice perspective on symmetry breaking charge separation in null aggregates. Yeah, and these are the two things that we are working, and this is the title of my talk as well, in which he gives much more elaborate quantum mechanical picture of how this charge separation works in a symmetric pair. So I would share that one. Probably, like, I'm not that good at explaining all of that. Yeah, so what do we do in our group is to try to understand which are the dimers that can be stable, how can we achieve them through synthetic methodologies. We also do little bit of computation in order to see which are the orientations that can be stabilized a priori if you take randomly some aromatic hydrocarbon. In this particular case, it is perylene diimide, and the method that we used is something that was like established by David Sherrill from Georgia Tech. Is called symmetry adapted perturbation theory, wherein you bring two of the chromophores close to each other. You name them as H star dimer, wherein you have exactly one on top of each other. A little bit of twist, which is what we call as X dimer, and a perfect cross on top of each other, which is what we call as plus. And very clearly, we see a kind of trend that is generalized in many of the chromophores, let it be perylene diimide or perylene or pentacene, and few more examples that we have done. It turns out that a rotational offsetted chromophoric pair turns out to be the most stable, and the least stable anyways is the one that is exactly sitting on top of each other, which should ideally facilitate maximum charge transport and maximum orbital overlap. So in addition to this, we have recently developed interest in working on amorphous materials that we are creating, or I would say microcrystalline material, where we do solid state NMR and also 3D electron diffraction in order to get the structure, how these chromophores look like when they are in these microcrystalline material. And in cases where you have like very tiny crystal, 3D electron diffraction works much better than the X-ray diffraction, and those who are interested in working with that. And this is done in collaboration with Peter Brasda, who is very good at 3D electron diffraction, and we also have now started working with the company that sells the 3D spectrometer. Yeah, so the tools that we use are very much pioneered by two of the groups here. One is ultrafast spectroscopy, which JD does, and then we also started working very recently on single molecule spectroscopy, which we learn a lot from Professor Sudeepta Maiti and various other colleagues in the country. So these two being the case, I will slip the intro part of the single molecule. What do we look at it? Towards the end of the lecture, I will come back on this aspect. So let me just give you an overview of what we do in our laboratory largely. So one is to see what happens if you have an aromatic hydrocarbon and you put different functionalities in the excited state, how do they behave? And it is largely excited state dynamics of organic chromophores. It includes some of the biomolecules also, including the eumelanin monomer. We look at very strange crystalline crystal structures with chromophoric assemblies that are not often seen. And this is also some search that we do in our laboratory, and that sort of exemplifies here that you see this particular structure probably is reminiscent of the photosynthetic reaction center. If you have, let us say, 10 books, yeah, and you put it in a bag, usually those books will stack on top of each other. Yeah, those 10 books will never look radially distributed. And so is the case with aromatic hydrocarbons. When you try crystallizing them, they are bound to stack on top of each other, and never it should look like a radial distribution. However, in one particular case, at least that we worked on, we stumbled upon a particular structure where 6 of the chromophores that are nicely radially distributed, which are symmetric in nature. Yeah, so this is another interest that we have. And finally, some of our major interests lie on these peculiar chromophoric structures that we prepare. We try to understand the excited state dynamics of that. and one of which I will narrate in this particular slide. So let us imagine that you have graphene and you photoexcite that. It goes to the singlet excited state, and quantitatively it comes back to the ground state, releasing heat. So you will not see either fluorescence, you will not see molecule going to the triplet as well. However, you take the same elemental composition, fullerene, which is contorted in nature, and you photoexcite fullerene. It goes to the singlet excited state, and quantitatively it goes to the triplet excited state before it comes to the ground state. And this made us think that, why don't we have aromatic hydrocarbons slightly contorted like fullerene out of plane, so that it should promote intersystem crossing in such system. And this was, an excitement that we had several years ago, and we started working on it. And rightly in this direction, we prepared three of the molecules, a flat aromatic and one side twisted and two side twisted. And this was synthesized by none other than your colleague, Kalaivanan, in our laboratory. And it took about closely to 5 years in order to achieve this. And he was like really strong in doing what he wanted to do. And he never, stepped back. Yeah, so this is an interesting series of system. Upon photoexcitation of the first molecule, we notice that it goes to the singlet excited state and then comes back to the ground state. While if you are twisting it once, before it comes back to the ground state, from the singlet, it goes to the triplet and then comes back to the ground state with 10% efficiency of intersystem crossing. Now you twist 2 times, we notice that the efficiency goes 30% to the triplet excited state. As a function of twist in the molecule, we could clearly guide the intersystem crossing, and this was one of the first efforts that we were successful in designing something, and we experimented to see that indeed that is what is happening. So these are some of the examples, and we have collated some of our contributions in 5 of these reviews and perspectives, if you are interested in. And this one, we were quite excited that, Desiraju and Gavasotti collectively mentioned that only 4 ways aromatic hydrocarbons can assemble and stack on top of each other. And this was a paper that was published in 1989, a very well cited paper from India. And we also could figure out that there are 3 other possible stacks of aromatic hydrocarbons that you can have, which are nothing but cross and helical and radial, out of which one I will be elaborating for the rest of the talk. And this particular cover design says that it is only the tip of the iceberg that we know in the crystal engineering, although we believe that we have clearly understood crystal engineering, and there is a lot to understand. And we believe that what we have added is only like, few among what is to be known. And what I'll be talking to you about is the cross architecture from here is being elaborated in this particular tutorial review that appeared recently. Now, this is the answer to the question that Professor Maiti was asking. As you can see here, when you have a chromophoric dimer, there are solvents surrounded by it. At the time of excitation, possibly that, one of the chromophores may have a few number of solvents that are solvated, while the other one may have less or more solvents that are associated with it. In this process, you create an energy difference between 2 of these chromophores, which allows jumping of a charge from one chromophore to the other chromophore. But this is a very basic level of understanding, and this is where the analogy that I mentioned, if you take off all the solvents, symmetry breaking charge separation is not reported yet. And possibly because the hydrocarbons were not stable in the gas phase in order to achieve that one, which could be a challenge. And can we have in such cases a smaller hydrocarbon and do similar measurements, which is something that I have not seen in the literature. So this being the case, going forward, what was our interest is to have 2 of the chromophores that are stacked, which is cross to each other. So we started out discussing about the chromophores being cofacial to each other. The interest that we have is whether we have 2 of them that are cross to each other. And this is something, as you can imagine, if you go to a penguin book house or any book house that you may have somewhere closer to you, at the cash table that you see, sometimes some of the books are nicely kept on top of each other, which are like cross stacks. And you would suddenly notice that certainly the person who is there in the store would have worked on that in order to keep the stack like that. So it is an energy spending process in order to get a nice looking stack which are cross on top of each other. And the natural one, if you just throw all the books, it would, sit on top of each other as stack. Of course, you can make it disordered as well, which is the most natural one. Yeah. So if you see, to achieve such a chromophore orientation was a challenge by itself. And why we were interested in that is sort of summarized in this particular diagram here. And this is what was proposed by very famous photophysicist Michael Kasha. And as you see here, two of the transition dipoles, when they are sitting on top of each other with a little bit of translational offset, they would still couple with each other. And the coupling becomes stronger as they get head to tail, which means that, they are right on top of each other. There is also a possibility that these transition dipoles get rotationally offsetted, and then at 90 degree, it should not be coupling with each other in principle. In this paper that was published in 1960s by Michael Kasha, only the chromophoric interaction is being treated with the help of a Coulombic model, where only dipoles of the transition dipoles of the molecules being coupled are being considered. There is no other consideration for the spectral shifts between two of these chromophores. However, in the paper, it states that the charge transfer interaction between the molecules may also be important. However, that is not evaluated in the paper. So it was not that he was not visionary. It's just that at that time, computing or numerically getting the charge transfer interaction between two molecules were challenging in order to achieve that through theoretical methods. And this is where a Pavlovian statement becomes important. If you want a new idea, read an old book. So go as much as old possible, you get a lot of new interesting problems that you can think of. So this particular paper that was published by Kasha in 1960s became quite interesting to us, and we wanted to see whether a cross geometry of chromophoric arrangement can be achieved or not. And that is at this fag end, as you notice, two of the chromophores when kept on top of each other, how do they behave towards photo excitation? And this is what we wanted to know. Now, as you notice here rightly, the Coulombic coupling can be computed using this particular formalism, in which it clearly shows there is a 1 minus 3 cos square theta term, wherein if the theta is 54.7 degree, ideally it should have no coupling between the two, and this is what we call as magic angle. And therefore, if you have two of the transition dipoles that are sitting on top of each other, let us say at 54.7 degree, there should not be coupling between two of these chromophores. Now, to achieve this chromophoric orientation, synthetically, it is almost impossible unless luck favors you, meaning that you cannot design and get anything that has an angle between two of the chromophores with translational offset of 54.7 degrees. So this is where this particular area got slightly expanded, where can you achieve a 90 degree offset between the two so that these two chromophores will not communicate with each other. Now, going by that, as you see, the rotational offset is what is being shown over here. And if you go by this expression, the 90 degree angle will certainly not have any sort of Coulombic coupling contribution. So you can nullify that. Now you may ask a question. Right from the beginning, I was emphasizing on two aspects. One is Coulombic coupling, which is what you call as a long range interaction, but there is also a possibility that when things come closer, the orbital interaction would facilitate coupling between the molecules, and that is what you call a short range interaction. Now, these two in combination is what contributing to a chromophore coupling, which is what we call as interchromophoric coupling. And here, Frank Spano from Temple University in the last decade or so came up with a very simple proposition of how to compute the charge transfer coupling between two of the chromophores. So at a distance of 3.5 angstrom between two of the chromophoric units, it becomes pronounced, while if you separate them over a distance, it becomes diminishing, and it diminishes quite faster, that after 6 or 7 angstrom, it is almost non-existent. Yeah, and this is the formula that he mentioned in his paper in order to compute the same. And how do you do that? If you have homo-homo overlap, the whole transfer coupling is indicated over there, and then you have LUMO-LUMO overlap, and the electron transfer coupling you have when you have the product of the two divided by energy of the charge transfer state and the energy of the singlet state will give you the charge transfer coupling. This is the charge transfer coupling is exponential decay.
It's e raised to minus
Yeah.
half beta.
Yeah. And the total excitonic coupling is a combination of these two. So this particular expression is something of quite great excitement to us, where you have the Coulombic coupling and the charge transfer coupling. Right now, we believe that, if you are able to create a library of dimers and understand the deactivation pathways in these dimers, you would be able to know if there is strong Coulombic coupling, it should favor singlet fission. While if you have more of charge transfer coupling, it should favor symmetry breaking charge separation. We may be wrong, but we are trying to find a correlation between these numbers versus what we would see during the deactivation pathways. As you can imagine, the origin of these terms get associated to the singlet fission and the charge transfer process. Now, in this journey, like, we wanted test examples, and we started working on it. At least 5 to 6 examples that we have created, and we have quite an interesting pattern that we see. So out of the 1.1 million structures in CSD, probably by now it is 1.2 or 1.3, people synthesize a lot of molecules and keep depositing to Cambridge Structural Database. And in 2018, at least when we checked, there were no single aromatic hydrocarbon that showed that two of them would sit on top of each other. And that is where some of our group members started looking crystallography into greater details, and noticed that these are the possible arrangements of hydrocarbon called herringbone, sandwich herringbone, gamma motif, and beta motif. But there is also another interesting arrangement that came up when the crystal structure of benzene was reported at a lower temperature, wherein two of the benzenes would sit on top of each other in a T-shaped manner. Yet there was no report on a cross arrangement of two of the chromophores, which is what we were looking for. Now, meanwhile, we saw an interesting paper that was published in 2018, where two of the chromophores accidentally got crystallized with magic angle of transition dipole orientation that you see over here. Now, which ideally means that if you go by the approximation of Kasha in 1960s, when these aggregates form at an angle of 54.7 degree between the transition dipoles, the aggregate should have the properties similar to that of the monomer in solution, which means that there is no other contributor to the spectral shifts when chromophores come close to each other. But indeed, that was not the case. These aggregates had clear spectral shifts, stating that charge transfer has a major contribution to the overall shifts when the molecules are aggregated in comparison to the monomer equivalent of that. Since then, we started looking for various molecules that are oriented in different ways, all possible ways that you can think of. However, we achieved in getting this 90 degree between two of the chromophores, as you see. And these are the molecules that we prepared in our laboratory. And this molecule that is in the middle here ended up luckily crystallizing with a cross architecture between two of the chromophores, as you see here. What is the end result? I would bring your attention only to three of the data sets that are shown over here. One is the molecule in solution. This is the electronic absorption that you see. And then the next one that you see, which is overlaid on top of that is the crystalline sample of the same material, which has exactly superimposable electronic transition with very little perturbation. I would not say that it has no perturbation. Yeah. Now, likewise, if you take the molecule in solution and the crystalline sample, the emission also overlays and the fluorescence lifetime also is same. Now, let me bring your attention to two distinct phenomena that are reported in the literature. One is, if you take a fluorescent chromophore, you aggregate them, the fluorescence can switch off, which is what you call as fluorescence quenching. There is also another possibility that you have a fluorophore to begin with and you make a stack of them, the fluorescence shoots up. This is what you call as aggregate induced enhanced emission, which is popularized by Yu Guang Ma and Ben Zhong Tang from China, having even a journal opened up with the title Aggregate that has got an impact factor of 18 or so at the moment. Yeah, so you can imagine how interesting a topic gets for a short while, probably not for a longer time. Yeah, so this being the case, you have these two phenomena. While in our case, what we are trying to propose is that you have a designed fluorophore and it has certain fluorescence properties, but then if you aggregate them, it retains the same property. So it doesn't have either decrease or increase, but it retains the original property, which indeed is what we see in this particular case. Now we asked a question, is it by a fluke that we got this system for once and can we get it again? Yeah, because by design it is very difficult. At the moment we don't have any sort of control over this. So then came Ligina in our group. So the first cross chromophoric arrangement was achieved by Ibn Sebastian, who is currently doing postdoc at Cambridge. And MB Ligina recently joined the Royal Society of Chemistry. And in her thesis, she figured out that pendacenes can exist as a cross chromophoric structure, and 3 of them are indicated over here. By this time, we started knowing how to compute a little more than what we used to know in our laboratory. And in all these 3 configurations, we ended up getting the Coulombic coupling and the charge transfer coupling so negligible that you can almost ignore. I mean, of course, this particular computation says that there is no coupling between the two, which is quite a common sense that you can think of. 2 of the chromophores that are crossed to each other, neither transition dipoles will couple, nor there will be charge transfer coupling, and that's what indeed the case is.
Are these representations atomically accurate? I can see some nice twists. Are those?
These are crystal structures.
Crystal structures.
Yeah, and
so yeah. So I was going to ask if why are those nice opposite twists and what actually induces the twist?
You mean on the edges?
For one molecule. He's asking for one molecule, whether it's the twist or the side chains.
Yeah. This one.
Right. Opposite, exactly.
Okay. So if you take bare pendacene, which is what, many of the laboratories, they use it for singlet fission. When you just want to assemble them, on either side, when you put these biaryl units, we believe that it is the CH pi interaction of the edge of one of the units interacting with the pi surface of the pendacene that is lying below makes this cross arrangement. So if we lift off that 2 phenyl groups, we don't see the cross. So this is the only clue that we have in design that can bring 2 of the chromophores in this orientation.
Question is, if you look at the side naphthalene,
yeah,
you have a side chain. One is twisted up, the other is twisted down. He's saying, why is that?
Okay, yeah, twist? Okay, that part I did not get. I mean, certainly we don't have answer for that. Only thing that we can say is that it is an extended infinitely periodic stack. So you have, let us say, one unit and one of the clips is facing this side to accommodate a pendacene from this direction, while it is facing the other direction in order to put the pendacene from other direction so that it keeps repeating. Yeah, so that it is more of a trans type organization than a cis type organization. This is possibly that, I can think of, but we certainly don't know. I did not notice that part yet. Yeah, so we have this total coupling being almost negligible. we clearly notice that in our second test case also, we have the crystalline state and the monomeric solution overlaying the electronic absorption and electronic emission right on top of each other, which validates like what we thought. In the case of cross aggregate, there will not be any interchromophoric coupling between the two. Now, I'll move forward in order to give a very small library of molecules that are prepared by several groups in United States and Europe. So if you take two of the chromophores that are linear, this is from a group in Colombia, Adams and co-workers. It is, I think, in this group where 5 minutes, yeah. It is in this group where Professor Arindam Chaudhary did postdoc, and this group has contributed a lot of interesting fundamental work in chromophoric systems. So here, Utnar and co-workers prepared a cyclophane that has two of the PDIs that are sitting on top of each other. Andongshi and co-workers took a lighter route of preparing simply a linear analog of chromophoric dimers. And here comes one of the most challenging in this area, where a trigonal Perlin diimide trimer is being prepared by Fraser Stoddart, and the photophysics has been looked at by Waslewski and co-workers. Now, we were interested in bringing two of the chromophores that are cross to each other. So that is what our interest is. And as you could see, that if you take a crystal of the cross chromophoric architecture compound and put it in solution, you never can confirm whether it is cross aggregate or cofacial aggregate or anything of that sort. So therefore, we decided to have two of the chromophores separated by a spiro bridge that you notice here, which precisely brings two of the planes at 90 degree between two of the chromophores. And that's what was our design. And this was achieved by Ebin in synthesizing it. And you notice that this is the crystal structure that is shown over here. And this picture gives a representation that upon shining light, it behaves more like a monomer, which means that it is a null exciton between two of the chromophores. There is no communication between each other. Now, you put this in three distinct solvents. So I will just run through quickly on ultrafast spectroscopy that we performed on these material. You take this dimer molecule and photoexcite in non-polar environment, which is toluene. We get only the singlet excited state decay of one of the chromophores. So it just goes to the excited state and then decays back to the ground state from the singlet excited state. While if you have slightly more dielectric constant, which is THF, you have charges being little bit polarized to the second chromophore. However, there is no full charge separation. And this is technically called as symmetry breaking charge transfer state rather than charge separated state. And that is what we noticed here. While in the case of acetonitrile, which is clearly a polar solvent, this is where the role of solvent comes into picture in creating the symmetry breaking state. And we see clearly two distinct peaks, and that have been deconvoluted to distinct species that are decaying down to the ground state. And those are radical anion and radical cation of two species that we have. And clearly the charge separated state thus created survives for longer time by virtue of the fact that you have two of these chromophores in two distinct planes. And because of that, the charges thus created has less tendency to recombine. If it were on two same planes, it would have recombined faster. So there is a little bit of twist induced phenomenon that we see in terms of surviving the charge separated state. I will move forward in order to show another exciting example that we prepared in our laboratory. You have two of the chromophores right now that are connected twice instead of once. And that is what you see over here. This is one bond and this is another bond. And as you see here, this is the crystal structure. And in this particular case, you take again the measurements in acetonitrile. You notice that the charge separated state created is like really long lived to the extent that the charge recombination to the charge separation is having a ratio of close to 11,000, which is like really long. Yeah. So which we believe that when you have two connectivities between the chromophores, the reorganization energy drops down and it has got a Marcus behavior in order to create the charge separated state. So fast charge separation and a very slow charge recombination that we see in these systems. Now, again, moving forward to test our hypothesis whether if you have two of the chromophores connected in a very loose manner, what will happen to the charge separated state created. So we connected it with one single bond. And we noticed that upon photoexcitation, molecule reorganizes in order to get an Excitonic-like state wherein we don't see charge separated state surviving for longer time. And some of the representative data that I will show here, originally it goes to the Frankel exciton state and then it goes to a hot Excitonic state, relaxes to an Excitonic state before it comes back to the ground state. In this process, we don't see anywhere the charge separated state being created. And this is what the summary of the entire photophysics that happens in a given dimer, wherein we don't see charge separated state unlike the previous two cases that I have shown. Now, if I may take 2 more minutes, there are two other possible orientations that we got excited recently is a chiral dimer of the PDI. So on a chiral support, we put two of the chromophores and see what happens if we have the photoexcitation done on these dimers. And you see here, this is the characterization for chiral dimer of PDIs, which we do circular dichroism and circularly polarized luminescence. And we clearly see that it leads to reduced and the oxidized species from the acetonitrile and high polar solvent that we have performed. The rates and yields of these processes, as much as possible to be determined, we have determined, and I'll be happy to discuss that if you are interested in it. We also performed some single molecule measurements on these dimers, and we have some preliminary exciting data to classify them into 4 different types of blinking patterns that you see in these chromophores, and wherein one thing we clearly see is that wherever long off states are there in multichromophoric system, it belongs to a non-radiative decay pathway, which is symmetry breaking charge separation. While the cases that has triplet population in the chromophores, we see short off states. And if we have coexistence of triplet and the symmetry breaking charge separated state, we get much longer off states. And this is something that we have understood in the last few months in terms of the single molecule data. So coming back to the original slide we started out with, this is the diversity that I started out wherein placing two of the chromophores in different orientation, pretty much we are getting all possible pathways that you see depending upon how they orient with each other. Probably I missed one of them, wherein if we have two chromophores that are crossed to each other in a very short time scale, Vivek Tiwari from IISER could see coherent oscillations in these molecules, which eventually lead to charge separation in a longer time scale. So you begin with coherent oscillations, and then as time progresses, it results in charge separated state. It recombines sometimes to triplet state, sometimes to singlet state, and it gets back to the ground state. And this is something that at the moment we are excited about, and there is a new addition. There's a paper that got yesterday accepted in JFISChem letters, wherein we have 3 of the chromophores that are put together. So as you notice that in the beginning, like I was only talking about dimer, now what if we have trimer? And in this trimer, we clearly see that this long off state at the single molecule level C, we see is a combination of SBCS and triplet. And using nanosecond transient absorption measurements, we can see 64% of triplet yield in a molecule that otherwise in a single unit does not show triplet at all, which means that it shows only fluorescence. Now, it also brings to the fact that, you take a molecule, make an assembly of it. If you don't know how the assembly looks like, you can possibly get everything out of it, either singlet or triplet or charge separated state or Excitonic or whatsoever. Provided we know what is the orientation that exists in these systems, very clearly we know what you can expect out of it, whether it is an eximofluorescence or charge separated state or associated deactivation pathways. These are some characterization. So what I spoke to you today is summarized in this particular tutorial review. If you are interested in this, would not have been possible without the support of large number of PhD students, and as I already mentioned to you, one of the PhD students you are well aware of, and and then there are a lot of postdocs who worked in our group in order to contribute to various things in terms of synthesis, doing computations and spectroscopy. And these are undergraduate students. And one good thing about IISER system, which I'm very thankful to, is about the interest of the undergraduate students right after +2 while joining in our place. They stay on for 5 years and they do almost equal to the things that are achieved by the PhD students, because it is 5 years of stay. And I'm very much thankful to many of the students who have contributed to various projects here, and they are in different places now. Thanks to IISER Thiruvananthapuram for generous funding and support. And I will be happy to answer any questions that you may have.
The talk is open for further questions. Yes, we will start by your formal grandchild.
We met once, yeah.
In the circular orientation, what is the interaction between them?
In the
Circular oriented.
yeah, there are several bromine atoms are present, and there is bromine halogen interaction, which is considered to be very feeble and weak, but multiple in numbers. We brought about 6 of the halogen atoms together, and it's called Br6 synthon. And since then, we also have another activity: how many halogens you can bring closer together in order to stabilize a crystalline system. And we have figured out up to 8 we have seen, and we also have interest in that. So it is purely halogen interaction.
One more doubt is, like you told, that is in the solid state, and we can't detect the spectroscopy of it.
Which case it
there is a colored compound, melanin.
Yeah,
Melanin
yeah.
compound. So can we do FTIR and try to analyze?
Possible. I mean, you get little bit of information from
FTIR.
solid state FTR. Likewise, solid state Raman you can do, but then you don't get a comprehensive picture of what is present in this solid. And therefore, at the moment in the literature, it is just proposals. Some of the authors draw 4 of the dihydroxy indoles in a linear fashion. Some like to draw it in a cyclic fashion that it looks like porphyrin. So it is all imaginary structures, and there is no proof for it. So there requires a little bit of attention to see like how those structures are. It's horrible. Yeah. Yeah, and Bern recalls that as a possible carbon dot that is formed in our body. Yeah, which is something difficult to believe. Bern is a good friend of mine. But then he almost comes to a point that dihydroxy indole can form carbon nanodots in our body, which is why, we are colored. So,
Thank you.
Yeah. So very nice talk. So I was just curious. So you discussed the orientation aspect and its impact on excitation formation. But what about, say, transport of an excess charge, like an electron or a hole?
Yeah.
Does orientation matter there?
Ideally, it should, because one of the problems in organic materials for the charge transport are defects, meaning that you expect these molecules to periodically arrange for longer distances, and 1 or 2 of them missing in between, you cannot have charge further going. So which is also something related to orientation, because you don't have a chromophore at all. Now imagine a situation that you have part of the chromophore in between, or like you have even further, and you have a full chromophore in between. Each of those would give different results in terms of the charge transport that you can generate, which also means that the organic semiconductor area suffers from the fact that you cannot get intact structure as you see in the crystal structure in any form of preparation of the sample except the crystal structure, which is crystal itself. So if you take, let's say, thin film, it gets really challenging that in thin film, first of all, you lose the third dimension, and then you are remaining with the 2 dimensions, in which certainly you cannot take the crystal structure as the structure in it. So therefore, something will be distorted in a manner that you may not get long range transport. But the advantage in organic materials is that you can easily prepare the monomer in different ways, and you can easily process them because they are soluble. And inorganic materials, to that counterpart, they are very difficult to process. So the challenge does exist that are these molecules like really stacked, like the way that you see in the crystal structure?
Okay, Mahesh.
Sure.
Yeah, I have two things.
Yeah.
One is that this different the aggregates that you are making with different orientation.
Yeah.
Is it a solvent effect? Like you are tuning? How are you tuning this orientations?
So it's purely empirical and it's hit and trial. You have seen like the number of group members that I have. So it allows me to at least ask one student prepare 3 molecules, and over a time, like I have 300 or something, which is a big library, and out of which some form the cross and some do not at all.
But I mean, is it identified like, okay, so for this kind of condition you have?
Yes. So once that forms in a given solvent, it forms always.
Okay.
Yeah. And in some cases, it forms in different solvents also.
So it's pure, I mean, it's kind of
it
a
depends
solvent
on the
induced.
structure of the molecule and the solvent that we use.
Okay.
But once you get it, you keep getting.
I see. Okay.
Yeah.
Good. The other thing which I was curious to know, you showed a database with some bar chart, the new molecules that are, I mean,
from the CSD.
Yeah. So how much is the Indian contribution? Is there any?
It is easy to figure it out. I will send that to you. It could be huge.
Oh, is that so?
Almost, I would say 70% is from UK. And those are the followers of Bragg and all the others.
Okay.
And India also has a big contribution on crystallography.
I see.
Yeah. But there is another database, which is what we call as PDB, protein database, and that has a large contribution from United States. And I think the base of which is located in United States. And there is another database which has largely inorganic molecules, and the base of which is located in Germany. And it has like, the historical evolution of who did well on that, and then the database got evolved there. Yeah.
So in a supramolecular framework where Coulomb coupling and CT couplings are internally compensated, so is that spectroscopically equivalent to your null aggregate or Greek cross?
In the cases that I have presented, in 4 cases, it is not compensated. That compensation is in another literature that is seen by Frank Wuthner and co-workers, where you have, let us say, the Coulombic coupling between 2 chromophores as 400 per centimeter or so. And then you also have charge transfer coupling, which has equal in magnitude but opposite sign, minus 400 per centimeter or so. They cancel each other in order to get a null aggregate. In our case, to begin with, both charge transfer as well as the Coulombic coupling are weak. So there is no cancellation that is needed. The summation also result to a very small number per se. Yeah.
Okay. Any further questions? Okay, just last question, if I can ask. It's related to the fundamental part of making an aggregate. Do you now have a good idea as to what solvent scope exists for different, or can you have a framework to define that you can tune through just the solvent, the aggregation propensities in an aggregate?
Okay. Yeah. So this is.
I know it's a hard question.
No. I mean, this is still, these things are at an empirical stage. Yeah. So in 2012-13, I started working out with a student who managed to get a compound in 3 distinct solvents, 3 different crystal structure we got.
Okay.
And this is what we define as polymorphs.
Right.
Okay. So I got a little bit crazy and greedy that I wanted the student to find out 7 different solvents in which 7 different forms of the same molecule we will get, and it will fall in 7 crystallographic systems, and nothing can be more exciting than
that.
this. Yeah.
The same molecule getting crystallized in different.
Yeah. And then from that 3 solvents we began, we tried 30 more solvents to get the crystal structures which belong to one of the 3. And nothing more was there.
Okay.
In certain cases, you get only one crystal structure, and no matter how many solvents you try, always it will fall on that. You know, there is no second polymorph you get. Now, this also brings to a question that, can you really design and get a polymorph? And the answer is no. At the moment, we cannot get it. So we only get when we get it.
But do you know the energetics of these polymorphs? Like are they closely separated or they are distinct?
Yeah, at least in one case, we did the potential energy scan, and we could figure out that some are kinetically stable, some are thermodynamically stable.
Okay.
The chief editor of Crystal Growth and Design, Jonathan Steed, recently ended up getting 6th polymorph of a particular compound that in England they really like it. I mean, you know, they keep getting different polymorphs. And he used a gel-based method to crystallize and got the 6th polymorph of that. And the title of the paper itself was 6th polymorph of you know, whatever, RBG dye or something like that.
Fine. Thank you very much. We will not serve you anything that is polymorphic. We will have very specific things in snacks. So let's have some snacks outside, actually inside the West Canteen. So thank you very much, Mahesh.
Thank you.
A big round of applause for Mahesh, and thank you everyone in the AV staff for putting the colloquium together. Thank you.